Well, good morning. So today we are continuing on with our forces unit, and I just wanted to remind you again, this was introduced at the very beginning of this unit, especially with Bill and I. He kind of hit law number 1 pretty hard. Remember Newton's laws of motion. The first one says an object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an unbalanced force. So if you think back to kind of what we were talking about yesterday, if the object is at rest, we know that the velocity is equal to 0 and the acceleration is equal to 0. If it's in motion, it's going to stay in motion. So that means it's going to be going at a constant speed, which means, again, my acceleration equals 0. So in the first law, we know that if F equals ma, bringing you down to the second one, if the acceleration is 0, then my net force here is also 0. So that means if I have balanced forces, so if it is balanced, my acceleration is going to be equal to 0, which means I'm going to keep doing whatever I'm currently doing. So if the object is at rest, it will stay at rest. If the object is in motion, it's going to stay in motion. Now remember that second part, the staying in motion, is a little bit harder for us to see here on Earth because there is one force, one little pesky force that is always acting even though we want to ignore it some of the times, and it's called friction. Remember, friction will slow an object down and will cause it to have a negative acceleration. Okay, so first law, we've been focusing on that. Remember, it is the law of inertia. Remember, inertia is the tendency for an object to keep doing whatever it's doing. Okay, so that means it's going to have a resistance to a change in motion. It's not that it has a resistance to motion, it's a resistance to a change in motion. And so we looked at yesterday on that quick little debrief, we had said, well, if I want to change my motion, then I have to exert a force, okay? Newton's second law is that my net force is equal to the mass of the object times its acceleration, okay? So again, if my net force is 0, then I know my acceleration is also 0. If I have an unbalanced force, so I do have a net force, then I will have an acceleration. And remember that acceleration could be in a particular direction, or it could also be speeding up / slowing down, okay? Newton's third law, we haven't really talked about this one too much. We'll kind of hit it more towards the end of the unit, but it's for every action, there is an equal and opposite reaction. And we had talked about when two friends high-five each other and the one is overzealous and kind of hits really, really hard, both experience the exact same force, so it hurts equally for both of them. So those are Newton's 3 laws of motion. All right, so a force is a push or a pull, okay? So just the basic definition of what a force is, it is a push or a pull. Now, all of our forces, we have a variety of different forces. We know that gravity is always acting on an object here on the Earth because the Earth has more mass than you and I, and so we get pulled to the center. It's the exact same reason when I drop a pencil, that pencil is going to fall down towards the center of the Earth, okay? Everything falls down. You know that saying, what goes up must come down, right? So that's because of the force due to gravity. All right, so when we are looking at forces, forces are always going to involve two objects. So for example, right now I am sitting on a chair, okay? And so my body is in contact with the chair. So between my butt, we had talked about this, there is some friction between my legs and my butt and the seat. And that friction there is what we call static friction. That static friction allows for me not to slide out of the chair. That's a good thing. Now, there's also a force of gravity. Gravity's pulling me down. So there's gravity. And then, do you guys remember what force pushes me up? Hopefully you guys are saying the chair, which you know that the chair is a normal force. Okay, so when I look at these forces and I have a force up and I have a force down, when I'm just sitting in the chair, my acceleration is 0. So my net force is going to be 0. So I am not accelerating up or down or left or right. So all my forces are balanced and I am at rest. So a balanced force, if the forces cancel each other out. So think about, like, again, we talked about sitting in a chair on the last one. Or think about any type of object that's on my desk. So right now my phone is on my desk. Okay. That phone is being pulled down by gravity, but being pushed up by the table. And remember that table is a normal force. Now, because my phone is not accelerating in the y direction, so y direction is up and down, x direction is left and right. Okay, so those ones should be from math. You should remember those two directions. Okay, so when I'm looking at my phone right now, it's not magically going to change its motion, right? Because that object has inertia. So it has a tendency to keep doing whatever it's currently doing. So it's going to keep sitting there. And it will continue to sit there until I apply a force. The moment I apply a force, and maybe I push the phone to the right because I'm pushing it over to a different person, that's going to cause it to move. It's going to cause it to have a change in its motion. Okay? So if I have a balanced force, the forces are going to cancel each other out. So if I had 20 newtons down, since it's at rest, I know that my force normal has to be 20 newtons up. And you guys saw that in your FET yesterday when you were looking at balanced versus unbalanced forces. Here's a good example. So if you're playing tug of war, dude, I loved tug of war in elementary school. Ugh, it was my favorite game. So with tug of war, if you have individuals pulling with the same amount of force, so this team is pulling to the right with 300 newtons, and this team is pulling to the left with 300 newtons. Well, if I do my net force, that means I want to find the sum of all my forces. Well, to the right is positive, to the left is negative. So when I add those two together, I'm going to get a value of 0. Or another way that you can think about this is look at the two forces. Are they balanced? If they're balanced, then you know the net force is 0 if they're equal. If they are not equal, so say for example in this one, I would say the force to the left is greater, and it's greater by 100 newtons. So you can either say negative 100 newtons or 100 newtons to the left. Okay? And then I could take this the next step and actually calculate the acceleration. Okay? So when we're looking at unbalanced forces, an unbalanced force will have an acceleration. It will have a change in the motion. So if I want a change in the motion, I need to have an unbalanced force. Okay? Otherwise, my acceleration is going to be equal to 0, and that can either happen because you're at rest or because the object is currently moving at a constant speed and stays moving at a constant speed. If an object has an acceleration, the forces are unbalanced. Okay, so just keep that in the back of your head. And then I know that the object in this one, so yesterday you had a couple questions on your FET, and it said, well, in what direction would it accelerate? Well, because the force is greater to the left, it is going to accelerate to the left. Okay? So then I could go ahead and start inferring, well, what is the motion going to be? Again, we're trying to take this to the next step. I know you guys know a little bit about forces now, but I want you to start realizing what is the connection to the observable motion. Okay? So our take comes from our FET. Again, our net force is equal to my mass times my acceleration. So if the forces are balanced, remember the net force is 0 because they're going to cancel out. So an object at rest is going to stay at rest. An object in motion continues in motion at its constant speed. If it is unbalanced, force net is not equal to 0. So my acceleration is not equal to 0. Okay? So if we're looking at net speed, if the net force was greater than 0, our speed should increase. If it's less than 0, speed should decrease. Okay? And this one, especially yesterday, you had an example that looked like this. And we had friction to the left. Okay? Our up and down were balanced. Let's say maybe it was 40 newtons, 40 newtons. Okay? So rather than saying the acceleration is to the left, we'll know the acceleration is negative, and it's going to be negative because it's going to slow down. So remember, I had tried to get you guys to start making that connection that if you have friction, friction causes things to slow down. It's not going to make the object actually accelerate in the left direction. So remember, with our vector quantities, it can be kind of tricky when you're looking at, well, is it accelerating in the positive direction or negative direction? Does that mean it's because it's moving to the right or up, or is it because it is speeding up, or is it moving to the left or slowing down? So you got to be really careful and kind of factor in, well, if I have friction, what effect does friction have on my motion? All right, so our free body diagrams are what you guys have started to see with this. Okay, this is a free body diagram. It diagrams all the forces acting on an object. Now, if the force due to gravity was stronger than the force normal, I would draw that with a bigger arrow. So I use those arrows and try to draw them if they are equal, approximately the same size. So it shows the amount of force and then also the direction in which the force acts. Gravity will always be acting down. Typically, our normal force will always oppose gravity and act up. So that normal force, again, could be a chair, it could be a table, it could be the floor. But for the most part, unless if we are skydiving, most people in cars and trucks and things like that don't accelerate in the y direction. They tend to only accelerate in the x direction. So these are the forces that we had introduced yesterday, and we didn't get a ton of time to talk about them, but you guys were able to kind of pinpoint different forces that are possible. The first one was the applied force. This is a force that you personally apply to an object. So if you are pushing or you are pulling, that is considered an applied force. Gravity is always there. The force due to gravity is always there, okay? So if you are drawing a free body diagram and you're like, I don't know what to put on my free body diagram, you at least need to have gravity. And then ask yourself, if I have gravity, is the object accelerating up and down? And if your answer is no, then you know you have a normal force that is going to be equal to my gravity force. Okay? So the gravitational force, reminder, we had said this yesterday, another name for the force due to gravity is my weight. And that weight is calculated by taking m times g. And we know that g is the acceleration due to gravity. So the equation F equals ma is still there. It's just we substitute in g because that's the acceleration here on Earth, which is 9.8 meters per second squared. And we want to make sure we start learning that number. So remember, 9.8, okay? Again, the normal force could be any type of regular contact force with a surface, okay? So if it is sitting on something or it's touching another surface, there is going to be a normal force, okay? Other ones, you guys know friction. Remember, friction opposes motion. So if I am walking to the right, friction is acting to the left. Remember, friction is sometimes a great thing that allows for us to drive on the roads without ice, making it easier to get to work. When it is icy, the frictional force decreases. So since friction goes down, then it's harder for us to drive, and that's when people start slipping and sliding. Okay? Air resistance is a type of friction. You might have heard this called drag. Okay, so air resistance or drag. If I drop something through the air, Typically, we will say neglect air resistance. And if we say neglect air resistance, that means that force is so small that's not causing much of a change with the motion of the object. But in all reality, is there air resistance? Yes. Tension was one that we did not know. This is one that was kind of harder for us to pinpoint. But tension would be, remember, if I had a speaker and it's being hung up by a cable, or if you think of like our stoplights, okay, our stoplights are supported by a cable, by a wire. If you think of like a gymnast on the rings, okay, they are hanging from those two rings, and those rings each are exerting a tension force on their body up, okay? Or think like elevator. If you're in an elevator, you have a cable that's pulling you up. That is our force tension. That's going to be pulling you up. Gravity's still going to pull you down. Okay? So tension, again, anything type of rope, cable, wires, and it usually opposes gravity. So when I take a look at a free body diagram, again, the size of the arrows tend to indicate their magnitude, so the number associated with this. So even though I don't have numbers on this, do you see how in the y direction my normal force and my force due to gravity are fairly equal? So I would say that they are probably balanced in the y direction, meaning they are not going to accelerate up or down. To the left and to the right, in the x direction, my forces again are also balanced, meaning that they are not going to accelerate in the x direction. So now the question comes, well, if my forces are balanced, that means that my force net equals 0, which means my acceleration equals 0. All right, so here's the million-dollar question. Is this object at rest, or are they moving at a constant velocity? The way you can answer this question is by looking at friction. Friction opposes motion. Not only that, take a look, there's a force applied, so I am pushing the object to the right. So that means that this object has to be moving at a constant velocity or a constant speed with an acceleration equal to 0. So it's not that it's at rest. This one is actually moving at a constant velocity. If it was at rest, we wouldn't have saw friction and we wouldn't have saw force applied. It would have just looked like that. All right, so when you're taking a look and you're asking yourself, okay, well, what is my force net? Okay, remember, if the forces are balanced, my net force is 0. So look at this first one. Force up, force down. Okay, are these two equal? No. And my net force, I can either go positive, negative, and then add them. So a positive 1,200 plus a negative 800 will give me 400 newtons up. Or I could just say, okay, well, the force up is bigger than the force down by 400 newtons. So it's either way, it does not matter. You can either put a plus sign or you can say up. The units for force are newtons. It gives a little bit of respect to the work that Isaac Newton did with our laws of motion. So that's why that is there. So if you take a look, this would be like an elevator. I have tension, I have gravity, so in what direction would this accelerate? It would accelerate up, and I could calculate that, and that's kind of where we'll go in a few days. All right, next one, my net force. If you look, my forces are not balanced. The force down is greater. It is greater down by 200 newtons. So I could do it that way, or remember, I can go positive 600 plus a negative 800, and I'll get negative 200 newtons. Okay. So for this one, their acceleration, they are going to accelerate down. And we will calculate eventually that here in one of the days. All right, take a look. Y direction, net force is 0, so that means I'm not accelerating up or down. But look left and right. Are my forces balanced left and right? Hopefully your answer is no. and my net force is negative 20 newtons, or 20 newtons to the left. Now, because my net force is negative, I know my acceleration is going to be a negative number. And it's going to be a negative number because either is it accelerating to the left, or is it because it's slowing down? So look back at your picture. Look what force that is. It's friction. Hopefully in your head you're saying, hey, it's going to actually slow down. It's not going to accelerate to the left. It slows down. Okay? So looking at those free body diagrams, that's where we are going to start to gain some of that information. So for today, what you guys are going to do, you're going to be practicing drawing free body diagrams. Every free body diagram, each object, I don't care if it's a phone, a book, a laptop, an iPad, a car, is drawn as a square. If you want to put a dot in the center, you can. That center represents the center of gravity of that object, okay, the center of its body. When you draw your forces, you're going to draw your arrows in the direction of that force. So for example, gravity always pulls something down, okay? And then I would draw a force normal up, okay? You might see a picture like this, but typically you do not see it drawn in this manner. And the reason is because this looks like gravity is pushing on the specific object down, whereas in all reality, gravity pulls our body, it pulls our mass from our center of mass down. Okay, so no to that, yes to this one. Okay, so as you guys are going through, really look and consider and try to identify if it says that they are motionless or you see constant speed. That should be going off in your head that, hey, that means that my forces are balanced. And then if you draw it and you're like, hey, they aren't balanced, you need to say, well, what force am I missing? Use your abbreviations. Start getting used to those. We have our force due to gravity, our force due to friction, our force normal, our force applied, our force due to air resistance, and our force due to tension. So we want to start using those abbreviations for each of them. If it says neglect air resistance or neglect friction, that means you don't have those forces in that scenario. Okay? So if it does say neglect something, just go ahead and ignore that force. We know obviously here on the earth, we would have those forces, but there are some that are there just to get you to practice with those free body diagrams using different forces. Okay? All right, once you are done, you do have a concept check in with me. A group, I will see you back on Monday. B group, I will see you actually tomorrow on Friday again. So if you have any questions, please bring them with you. Definitely double check. Make sure you're reaching out if you have any questions thus far. Okay. You guys have a great day.